Good evening. Tonight we welcome Don Andy from the Sierra Nevada in Spain. According to the notes, he's a fifth-generation coal miner from Wakefield. He was educated as a mining surveyor and as a chartered mining engineer, and was a colliery manager in Doncaster and in Scotland in the 1990s. He also says that he became interested in astronomy from an early age due to having a bedroom with no roof. That must have been a problem when it was raining, Andy. And later started with binocular observing until he got his first serious telescope in 2004. He became a member of MSAS in 2006, and as usual, everything's gone downhill from there. So he's proficient in outreach activities in English and Spanish, and he had his first article in Spanish published in November 2013, and has recently just had a book accepted. In fact, I think it's been published now on mining in the Spanish regions, both in English and Spanish. So, ladies and gentlemen, can you put your hands together and welcome Andy Devey?
Thanks for that, Roy. It's a bit out of date. I've had 4 books published, 2 in English, 2 in Spanish, and a 5th online. So it's a bit out of date, that one now. Okay. I will share my screen. Okay, can you see that okay, Paul?
Yes, we can.
Okay, I'll start. Right. I'm going to give you an update on solar cycle number 25, which at the moment, we're just over halfway through it. So it gives us quite a good chance to see how it's progressing. So I'm just going to skip right back to the beginning, because solar astronomy with telescopes is just over 400, just under 415 years old. Now, many people think that Galileo Galilei was the first one to point a telescope at the sun, but he wasn't. An Englishman called Thomas Harriot actually did that on the 8th of December 1610. But his notes remained undiscovered for, I think it were a couple of centuries before this was actually proved. And he actually observed some sunspots, as you can see his drawings, and then the line in between, the lower drawing, that refers to January the 14th, the following year, which was 1611. Both of these observations predated Galileo, and unfortunately, members of his family were associated with the gunpowder plot 5 years before in 1605. So he didn't publish because he didn't want to draw attention to himself, because back in those days he preferred to keep his head. So that's why he remained unpublished, and it was later work that actually discovered this. So in 1612, Galileo Galilei pointed his telescope and did some detailed drawings. And since then, people have been able to orientate them and do a rotational animation based on his sketches, which you can see here. But if you think about it, when you look at these drawings from Galileo, 1612 was obviously a stronger part of the solar cycle from Harriot's drawings about 18 months earlier. And if either of them had pointed a telescope at the sun and it would have coincided with solar minimum, sunspots may not have been discovered for 4 or 5 years later, because during solar minimum there are very few sunspots. So the solar cycle, which I've mentioned, we're on cycle number 25, and the sun has a a magnetic period of 11.3 years. But it's actually double that, because after each cycle, the sun flips polarity. So north becomes south on the magnet and vice versa. So a full solar cycle actually is about 22.5 years. Now, Samuel Heinrich Schwabe is the German astronomer that discovered the solar cycle through his extended observation of sunspots. And later, Rudolf Wolf, the Swiss astronomer, he did some work projecting it back. So he was reconstructing solar cycle activity. So this next drawing shows you from when the very first telescope observations were made in 16, 10, 11 and 12. So those are the red crosses, because there weren't enough observations on a continuous basis to show detailed cycles. But when you look at it, you can infer the space in between them was the same. And then you have this period in the mid 1650s to 1700 when very, very few sunspots were actually recorded. And later work by Maunder named it as the Maunder minimum. Now, there's been another minimum since, which was the Dalton minimum in around about 1800. And then there's been the modern maximum, as you can see on that graph. Now, the previous cycle, if you look to the right-hand side of the graph, which was cycle 24, was one of the weakest, as you can see in modern times. So those peaks are sunspot counts. And the one to the right of it is the present cycle, but the graph is not complete because we have gone way over 200 sunspots. So it's been much stronger than predicted, as you will see shortly. So I spoke about sunspots, and what they are concentrated bundles of magnetic field that comes through the sun and out into the solar atmosphere. So the temperature around these magnetic fields is slightly lower than the rest of the photosphere, or the sun's sphere of light. Now, the normal photosphere is about 5,500 Celsius, whereas the centre of the sunspot, which is called the umbra, is round about 3,500. So yeah, it's not cold, but it is colder than the rest of the photosphere. And then the grey areas round it, that's called the penumbra, where there are lines of fibrils where the plasma is moving from the outside of the sunspot in towards the centre of the core. That's a phenomenon I'll show you called the Evershed effect, which you'll see shortly. Now, this particular sunspot, I've chosen this one. It occurred on the 3rd of March, 1947. I know this particular photograph shows it on its next pass when it come round for a second time, but its area was measured as 4,300 millionths of the visible surface of the sun. Obviously, the visible surface, we're only ever going to see one hemisphere of the sun. So sunspots are measured by their area. And when it came round again, it was renumbered. So often sunspots are renumbered on the second pass. So just to give you a comparison in size, that's from the 7th of April 1947, and as you can see, the area of that sunspot is round about 2 Jupiter's diameters. So these are enormous things, and they harbour a lot of magnetic energy. Now, the other thing about this photograph, this is from a professional solar telescope back in 1947. So only just over 70 odd, sorry, just shy of 80 years. So what you'll see next is, that's my photograph of the largest sunspot of the previous cycle, which was cycle 24. And that covered an area of 2,710 millionths of the solar disk. So it was only just over half the size of that previous one that I showed you. But this particular photograph is done, it's a 12-panel mosaic, done with only a 90 millimeter solar telescope that's tuned to the calcium K, or the blue part of the spectrum. So, and this is me as an amateur working from an observatory at home outside my house in Spain. So that's a white light image of that same sunspot. And all my photographs and animations, I always orientate them to correct solar orientation, but also I put the date and universal time. So it gives them scientific context. If you fail to date and time your work, you get a beautiful, pretty picture with no context. So always record everything that you do as accurately as you possibly can. So what I've done there is, there are quite a number of wave bands that are available for solar astronomers. You can get a spectrograph which you can tune into different wavelengths. But what you see here is the image on the left-hand side is in white light, and that's done with a TOA 130 telescope, very similar to the one that you've got in the observatory. So if you want to put a Herschel wedge on that, you will be able to do some high resolution photography in white light. So with white light, you can see all the contrast of the sunspots and some of the lighter plage areas around them. The center image is from a 90 millimeter Coronado CAK telescope. Now, what you're doing here is you're looking into the lower chromosphere, which is an area above the photosphere, but not to the upper chromosphere, which is what the right-hand one in hydrogen alpha shows. And in that level, you see all the huge plage areas and the large chromospheric network, as well as all the individual convection cells, which you'll see in calcium K, and also you can see all the individual convection cells in the white light image. So the one on the right is the upper chromosphere, which you see in the hydrogen alpha telescope, which again in this case is 90 millimeter. And I'm fortunate to have a double stack version, which allows the features to stick out more. But if you look in hydrogen alpha, the sunspots are far less impressive than what they are in both white light and calcium K. The difference is in calcium K, as you'll see shortly, and also in hydrogen alpha, we can very easily photograph solar flares, even the very small ones. Now, solar flares can be seen in white light, and one of the challenges for us BAA solar section members is to try and photograph or image white light flares. Now, to date, I have never seen a white light flare. The drawings from Richard Carrington from 1859, which were 1st of September, he was the first discoverer of a solar flare using white light. and that was corroborated by a second observer. So he was credited with the discovery of solar flares. So just with those three images, it gives you an idea as to what is available from the easier solar telescopes to buy. There are more exotic ones, but because I've not got experience on them, I'm not going to discuss those in this talk. But it gives you an idea. Now, for younger observers, all three images you can see with your eye. Now, we tend to use monochrome cameras, which allows us to pick up the detail, and with monochrome you can use 100% of the pixels. Now, when I first got calcium K, about just less than 20 years ago, I could see a nice crisp blue image. Now, as you get older, the blue part of your eyes starts to drop off, and I can't see it anymore, but I can photograph it. So, just a few facts. Going back to June 1991, we look at solar flare activity, which is often very sporadic until you get a nice big sunspot. And that one, which was during solar cycle 22, they had a period from the 1st to 17th of June, which was filled with numerous intense flares. So that one region, the AR6659, it produced 5 X12 class solar flares and an X10 class flare. Now, I'm going to shortly go into the solar flare scale, and I'll explain that a bit more later, but jumping back to cycle, you can see cycle 23 and 24 there, and they were both classed as double peaked cycles because it didn't come to one point in the center. When you see the average graph, which is the darker blue line, it formed a double peak. And the yellow line on the right was the consensus prediction for the current cycle, which was predicted to be another weak cycle. So if these had gone down to nothing, there would have been another solar minimum. Now, I want to call that the Maunder minimum. I'd have called it the Maundy minimum because I, for one, would have been well peed off. Anyway, it hasn't occurred that. So, going back to those cycles, when they're predicted back, cycle 25 started in December 2019. So the minimum small sunspot number were down to 1.8. And this cycle is expected to continue to 2030. Now, at the moment, I'm 69 years old. I'm in good health, but with the cycle being 11 years, none of us know how many more solar cycles we're going to be about to witness. And if we're able to do that. So it was predicted to be weak, but as you can see, it's been stronger than predictions. So this is a plot showing you the sunspot numbers. And as you can see, we're just shy of 2026. So it's a couple of months out of date, but this is the most recent one I could get. So we've already passed the peak, but we cannot say for certain whether or not there's going to be another peak, which could happen over the next 2 or 3 months. If it doesn't, it's more likely it's going to be a single peak cycle, this one. And the bottom graphs shows you all the peaks of the earlier cycles, going back to cycle 1, which was in 1755, I believe. So, just showing you, because I see quite a number of new faces there, which obviously don't know me. So, well done, your lot. I'm down there near Almeria. We've been in this house since October 2013, but we've been in Spain since November 2011. So first thing I did within 2 months of building the house, of moving into the house, I built this observatory, which is a rollback observatory. So basically it's a 2.4 meter wooden cube that's reinforced with 19mm rebars, and it's fastened to the floor with those turnbuckles, which you can see just in front of the pier. And I open the door, which is on a 3-lock system. I lift a tongue plate out just behind the door, and then undo the floor mountings, and then I can push the whole shed backwards. And from leaving the house to imaging, if I've already got my laptop started, I can do it in 4 minutes. So I've never automated my imaging system for solar. So when I do any solar imaging, I like to be out in my observatory, and I either sit outside if it's winter with that, can you see that white box, which is my micro observatory on the table, and there's a little black blanket I can pull over my head so I can see what I'm doing, or I'm actually inside my observatory. So that's my view looking directly south. So we're surrounded by those grasses that you can see are called esparto grasses. And they're quite famous because from our area, back in the 1900s, they used to export 30,000 tonne of this, and it went through from the coastal ports into Tilbury docks, and it made all the newspapers in the UK. It was the pulp for all the papers. So this area was actually responsible for educating Victorian Britain, but that's just a throwaway fact. On the floor, I've put small chip-ins, and the grass and the pine trees that you can see on the hills behind have a good damping effect, which helps the thermal stability of the air in that vital 2-3 meters above the floor level. And often when I'm out, I will put big blankets on the floor to further help damp it, to improve my local seeing conditions. The battery pack, when we first moved here, our electricity system was a bit haphazard, so we got lots of little micro power cuts, which were really infuriating. So you'd lose your tracking. So what I do is I keep that constantly charged, or I used to do, and ran from battery power, so that even if we had a power cut, I could still keep imaging. So I swapped the EQ6 for this EQ8 mount, which is much better at carrying the load. And you can see there's a double stacked Hadron Alpha telescope, which is the right hand one. The TOA 130 is the central telescope, and this one on the left is the CAK. And with solar telescopes, the blocking filter, they are very sensitive to moisture. So even though it's very dry where we are, the telescopes, when they're put away, I take those diagonals out and keep them in a plastic box with a desiccant. So I only put those out when I am imaging. And that just shows you how it's completed. I've got a 60mm guide scope, and there's a little pointing laser there. And if you look at that little brown plaque to the left of it, that's the MSAS Southern Spain Observatory from the 2015 visit, which Paul were on, weren't you, Paul? So what my passion is, I really enjoy doing time-lapse. Now, this is in white light using the TOA 130, and I was actually imaging with two times Barlow, so I was at 4 meter focal length here. And when I'm imaging in white light, I will do about 1,000 frames, and then I go through autostack at 3. I've tried 4, but didn't like it. And I'd look quite a lot of failures, particularly if you get thin clouds coming across with autostack at 4. So I've stuck with 3. And I'll look at the performance graph and usually take the top 15%. So I'm just processing the best frames, and because all the bad frames that you put in detract from your image. Now, this particular animation runs from, as you can see, 11:02 to 13:18, so about 2 hours 15 minutes. And I speeded it up so you can see the bubbling of the convection cells, but if you look carefully you can also see the fibrils running in across the penumbra into the centre, which is the umbral region, as they are diving down, or appear to be diving down. Now, where you see the line connected across, that's what's known as a light bridge. So, and this particular sunspot, I've given its AR number there, it was about 7 times the Earth's diameter in size. So, if anybody's just got a standard telescope, either buy an Herschel wedge, which when I got mine, it was about 300 quid, but you can get some Barda filter paper for probably less than 30 quid, which you can put on the front end. And if you wanted, you could start doing some imaging sequences in white light to do some animations on the sun's convection. So this next one, this is calcium K. Now, this particular one's not mine. It's another guy who posts called Apollo Lansky. And when he were imaging, he were lucky enough to put to capture an X-class flare, as you can see there on that right-hand sunspot, in calcium K. So when flares first occur, you get a lot of brightening around the sunspot, and then you immediately get magnetic loops start lifting, and that's something you're going to see a lot shortly. So immediately after when I saw that, I went into calcium K the following day. Now mine have got, so I had 3.5 hours from 10 o'clock to 13:30 Universal Time, and you can see I were only lucky enough to catch some minor C-class flaring. But when you look at it in high speed, it's almost like a lightning effect. But the other thing you can see in calcium K, when you look just outside the penumbral area, look at how much activity there is in the convection cells immediately surrounding the sunspot compared to the other areas. It's almost like an exaggerated boiling effect. Now, I've not seen anything that explains that, but that's not to say it's not been written about already. So, I've mentioned solar flares. So, the strongest ones, they are the X-class or extreme flares, and they could cause severe radiation storms and global blackouts. They can overload satellite systems, and obviously, with that intense radiation, they can pose a risk to human bodies. And Apollo were very lucky that none of their missions went during extreme solar storms. So M-class or medium-class flares, they can cause brief radio blackouts and minor radiation storms and affect navigation systems. The C-class flares, they are too weak to notably affect the Earth, but they can still cause some radio communication degradation. And then B-class flares, they're the smallest and least impactful. So each class has a subdivision between C1 to C9, B1 to B9, M1 to M9. Now, X1 to X9 are classed as extreme flares, but anything above an X10 is classed as a super flare. And I'll come to some of them right at the end. So, there were some solar storms, big ones last year. in May. And because they are the biggest solar storms of this cycle, I'm going to concentrate quite a bit on that in the next 5 or 10 minutes or so. So there were a series of powerful solar storms with extreme flares and geomagnetic components that occurred from 10th of May to 13th during this cycle 25. On 8th of May, solar activity in that region was assigned number 13664, or as we call it, active region 3664, and that produced an X1 class flare and multiple M class flares, one of which I filmed and I'll show you shortly. And they launched several coronal mass ejections, CMEs as we're called. On 9th of May, the active region produced an X2.5 class flare, which I was lucky enough to film the whole thing from start to finish in great detail, and I'll show you that shortly. And the following day, an X3.9, which I also filmed. On the 11th, it produced another X-class flare, an even bigger one at 5.4, but as you can see, there were 01 universal time, so it was dark for me. So the people in Australia got that one. Now, the produced coronal mass ejections, now if it's a halo CME, that means it comes out, the sun's in the middle of a cloud coming towards us. So basically we're in the direct line of fire. If they're offset, they can miss Earth entirely and go off and hit one of the other planets within the solar system, which obviously we are not too bothered about. But when you get a big one that comes straight towards us, that's when we get problems. The strongest one occurred, which was an 8.7, and that was one of the biggest since blackouts since the solar storms of 1989, and I saw auroras from Wakefield then. That's the only time I've ever seen auroras. On the 10th of May, there were auroras over my head here, and you'll see some photographs of them shortly. And I really enjoyed sleeping through them. So this just shows you the X-ray graph from the 8th of May through to the midnight on the 14th of May. Now, this line's quite faint, but that's the X-class line there. So anything above that or touching it is an X-class flare. The biggest one, that was X8 point something, and that's the X5.6. So as you can see, it was a very active region. So what I'm going to do now is I'm going to show you what I captured. So I am using I'm at 1.6 meter focal length. So my telescope is a nominal 800 millimeter focal length. So I've got a 2 times Barlow screw in there, and I'm using a ZWO ASI 1290 mono camera. So I don't know how clear, this is very high contrast and high resolution, but over the internet, I've no doubt you're getting a lot of dilution at your end, but I can only show you what I can show you. But where we amateurs come into our own, there's some very sophisticated satellites monitoring the sun. One of the best is the Solar Dynamics Observatory. And there are, I think, 10 or 11 very sensitive cameras on it. But unfortunately, in extreme solar flare events, immediately around the area of the flare, the pixels get overwhelmed and it gets drowned out and puts like a big cross on it. So we amateurs, we are able to show the more fainter detail associated with the flare. So we do play our part in solar science. And this current cycle, 25, I would easily say that it is the most observed solar cycle ever because of the sheer number of solar telescopes that the amateur astronomical community have. And both me and Mick, we contribute to the BAA Solar Observing Programme, the South African the Astronomical Society of South Africa Observing Programme, and I also contribute to a website called Solar Chat, and also I have most of my better images I put on the NOAA Space Weather website. So that's a M6 class flare. It weren't a particularly good seeing that, but that's just a white light photograph of the sunspot. And on that one, I forgot to put the date and time stamp. I think it was cropped off at bottom when I put it on. So sorry about that. But this one here, out of all the animations I've ever done, I can safely say this particular one's my favourite, because within 10 minutes of setting up, this X2.2 class flare started. And if you look very carefully in this area here, you can see all the magnetic loops forming straight after the blast. Now, best way of explaining a solar flare is you get magnetic energy which bends and twists. And imagine if you keep twisting an elastic band, eventually it will snap. And when the magnetic field snaps, the magnetic energy is immediately converted to thermal energy or heat. And the general photosphere around here, as I told you, is about just shy of 6,000 Celsius. And in the area of the flare, it jumps up to over 2 million degrees. So the temperature difference is enormous. So this is just about the geomagnetic storms. So the one was actually a G5, which is the most extreme solar storms. So as you can see, that scale, you've got the minor ones, G1, moderate G2, strong G3, severe G4, and then the extreme ones, a G5. And what the extreme ones do, they can actually bend the Earth's magnetic field. They push it down towards the Earth. And the one from 1859, the September one, the Carrington event, actually pushed the Earth's magnetic field below the soil level. So it pushed it into ground. So it wasn't given any protection. And back then they had the telegraph system, and all the batteries were disconnected, and it still worked because of the energy generated by the solar energy. And I believe there were 1 or 2 fatalities by electrocution off that. But any pipes or anything long wires, currents would be induced in such an extreme event. So, as I mentioned before, we did get auroras, which is the next slide coming. But what the auroras do, they excite the atoms in or the molecules in our atmosphere, and they change them into different colours. So green is the most common colour, and that's produced by oxygen molecules. And these are at altitudes that's lower than 100 kilometres. Red is also produced by oxygen, but that's at the higher altitudes, and that's above 200 kilometres. Blue and purple, they are created by excited nitrogen molecules, which the light's emitted when it's ionised, and then it's the different gases that's caused the variety of colours as these particles charge. Now, the more extreme a solar storm is, the more the auroras are pushed south in the northern hemisphere and north in the southern hemisphere. And I believe the Carrington event, the auroras were actually seen right down at the equator. So normally, under not so severe conditions, you may see them in north of Scotland I know a number of times they've been seen and photographed over Orbit Wentworth, and lots of people do cruises on the fjords in Norway and around Iceland to see the Northern Lights, well, the Aurora Borealis. So that's a photograph from Calar Alto, which is on the same mountain range as I'm on, and it's about 40 kilometres due west of my location. So we're at a latitude of, I'm at 37.2 degrees north, so that's about 37 degrees there. So the sunspot kept growing. So on the 10th of May, it reached 2,400 millionths of the solar surface. Now, up to now, I believe that's the largest sunspot of this current cycle. And if you compare that to the one that I showed you earlier from 1947, which were 4,300, this is only about 60% of the size of it. Well, it was, sorry. So the following day,
Andy,
that's me.
Can I just stop you there?
Yeah.
We lost your sound for about 20 seconds, and you were commenting about the size of that sunspot and comparing it to the maximum one observed.
Okay, I'll go back. Yeah, I'll go back. Yeah.
Thank you.
So, 10th of May, that was that sunspot, which was AR 3664. That is the largest sunspot we have had so far of cycle 25. It was 2,400 millionths. So if you compare it to the 4,300 millionths of that one from 1947, it's only roughly about 60% of the size of it. So not big by comparison. Now, the following day, we got a X3.9 class flare, and I just missed the peak of it, but you can see all the magnetic loops forming here after it? Now, the magnetic loops are more spectacular when you're able to see them on the limb, which I'm going to show you them shortly. So that was a 3.9. And then, just for good measure, I got an M8.9, so that's just under X-class flare. But with M-class flares, as you can see, sorry, I lost my, oh yeah. Can you see the magnetic loops forming across there? I'll let it run a few times. So that's the magnetic fields reconnecting. So this was from a different sunspot. So it was only a couple of days, 4 days later, and that was for a new sunspot emerging from the eastern limb of the sun. So when we look at the sun, the left-hand side, that's the eastern limb, and the sun rotates from east to west. So if we see a sunspot where that flare is, we can generally follow it for 14 or 15 days as it tracks across the sun. And obviously they are more dangerous for us when they are facing us. So if we get an ejection, we're more likely to be in the direct firing line. So that one you can see, I caught the peak of the flare, and then you can see how the magnetic loops continue, and the magnetic loops last right through the X-class and well into the M-class part of the flare. And if you look at that one, I was imaging it for an hour and a half on that, from 1536 to 1706 Universal Time. Now, I got that. A mate of mine, Mark Townley, he got it in calcium K a little bit later. So it's a good comparison of what you can see. So as I was telling you before, you can pick up solar flares in both hydrogen alpha and calcium K. So what we do is every day we look at the X-ray graph, see what we've missed, or if it's worth going out and spending a lot of time at observatory, or not even opening it up. And then if a big one's gone off, we're looking on all websites day after to see who's been able to capture it and process it. So when a big one goes off, it's quite exciting that way. So this one, it was only an M1 class flare, but what I've done there, I went to 3.2 meters focal length with it. So that's two times Barlow. Bearing in mind I'm only on a 90mm solar scope, and if I'm doing limb, I overexpose the photosphere so you can pick out the faint detail in the magnetic loops. And when the material, if you imagine the loop as an arc, the material, the plasma, it precipitates out and runs down each side simultaneously. So it's not coming up around loop and back down. It's actually, so you're actually seeing hydrogen rain there running down those magnetic field lines. So this next one, it was only an M4.3. So it's a little bit like fishing is solar astronomy. We look at the ground-based solar telescopes that's maintained by the Global Oscillation Network Group, or GONG, and there's an animation feature so you can see what's the most active part on that particular day. So it might be a prominence lifting off or showing signs of lifting off, or it might be an active region. We then look at the X-ray graph and see which parts flare in the most. Now, what I tend to do when I'm imaging, I try and keep an eye on both of them, because when I'm imaging, I'm trying to get high resolution in one small area. And if you don't, Sod's law is something really good will go off in a different part of the sun to where you're imaging. So what I often do is I may abandon one imaging run and go straight onto a different area that started exploding. So all I'm doing is I'm increasing my chances of actually trying to catch something. So another one, that was only an M4 flare, but as you can see, even the M4, they produce some really beautiful loops. Now that particular one, just concentrate on the loops and you can see the plasma running simultaneously down both sides of that loop. It's a good example showing you that, is that one. So this was I was lucky enough to be in right region, and that was an X1 class flare, which it was quite a short duration one. As you're looking there, I'm only imaging for 54 minutes, and the whole thing had gone, even the loops had gone by the time I'd finished. So the solar flares are very fleeting. So this one's not mine. A guy called Alexandros Francis, he was lucky enough to catch an X9 class flare. So it's pure luck. We know where we've got an active region. That one was on 3rd of October, and that's the largest flare we've had so far of this solar cycle 25. So for me, it's slightly over-processed, but people have got their own opinions on things, because we're looking at a gaseous surface. So if it's too harshly done, it can be over-processed. But I'm showing you the biggest flare because I'm just part of a very wide amateur community now. And when I first came to Spain, like 13, 14 years ago, there were very few people actually doing this type of work. And now there's quite a number of people. So this is one of mine, which was just shy of an X-class flare from 10th of November last year. And with that one, you can see after the blast, when I find my cursor, there's a CME gets flung out in this area. Now, some of them CMEs get space launched, but a lot of them get pulled back down because of the sun's gravity. So now, CMEs are not always caused by solar flares. What I'm showing you here is fairly high resolution of a prominence lifting off. So sometimes it's prominence eruptions. They come towards Earth, and they bring a lot of material. So some of the prominence eruptions, which are CMEs, if they're coming towards us, it's normally a filament. So the only difference between a prominence and a filament is how we see it. A filament is across the surface of the sun as we're looking at it, whereas a prominence is stuck up just on the edges, on the extremes. So just showing you a few things from this year, because this is one I did from June. So both myself and Mick, we are submitting images to the fledgling Astronomical Society of South Africa. But you can see all the convection cells, the penumbra, umbra, and when you watch the area boiling, all these sunspots are like fixed in position. They may drift slightly from one side to other, while all these convection cells boil around. And it's only through high-speed time-lapse that you can watch and just enjoy seeing such things. So what I'm doing now, I tend to do, I've got a Saturn M camera, which I use for white light, and at prime focus, which is 1 meter focal length, I can do a nice high resolution single image. Now, with that camera, it's a very big chip on it. So if I do say a 400 frame video set, it's comes out at 2.5 gigabyte. And with this slow clunking computer of mine, it takes about 25 minutes to put one image through AutoStack it before it comes out. And then what I do is I still use Registack 6 for wavelets for sharpening. Now lots of people use IMPPG, which I use, but I only use it for aligning sequences prior to animation, and I still do manual animation in Photoshop. So every one of them images and animations that you've seen, I've put myself through the pain and the time of doing them. So I can spend say 3, 4, 5, sometimes 7 hours imaging an area. I put everything through AutoStack, which means I can have something to eat and do other things. But once they're out of AutoStack it, I then have to put them manually through Registacks to process them. And I try and use the same wavelet settings, but if the scene's off, I can use wavelets to smooth them out a little bit. But then through IMPPG, that's quite a quick process to auto-align them, but it takes me quite a long time, up to an hour, to put the image together and spit the GIF out of Photoshop. So just showing you the number of flares, and this graph goes back to 1976, and the colours are, when I get my cursor back, I'm not bothered about the dark brown at the top. They are, I've got it. So the dark brown, they are X-class flares. The lighter brown there, they are between M5 and M9 class flares. And then the mustardy coloured, they are M1 to M4 class flares. So they are actually numbers of M flares. So, and you can see numbers on that side. So it gives you an idea of numbers. I believe we've already exceeded the number of X-class flares for the whole of cycle 24 already with cycle 25. And this is just a list of the biggest ones so far in the time. So you can see that X9 that I showed you. There were X7.9 limb flare. And there was somebody put a GIF out on that, which I've got, but it's 300 megabyte GIF. So what I tend to do is I might do a video run every minute, but when I put an animation together, I might only animate every third or fourth, or sometimes every fifth frame, just purely to keep the size of the files down. Because if you put anything on space weather, the maximum you can get on is 20 megabytes. So what I have to put on is significantly reduced in resolution compared to what I get. So I tend to house my stuff, the higher resolution stuff, on Astrobin, which seems to have its own compression file. So these are some of the top 50, and the 50th was still a X1.35. So we're over 50 flares now for this cycle. And then I'm just going to give you a comparison now to the strongest flares that have been recorded. So there were an X40 plus, which happened in November 2003. Now that was an enormous blast, but luckily it was right on the limb and it flew off and hit Venus. If that had come and hit Earth, that could have been another Carrington event or bigger. So literally we are dodging bullets all the time. Now, if flares go off on the far side of the sun, then they're not much danger to us. But with the SOHO satellite, there's an occulting disk, and you can see the enormous coronal mass ejections flying out and just going away from us. But still the best satellite for seeing the CMAs coming towards us is the SOHO satellite, which is, I think it's been going for over 30 years as that one. So you can see there's some very big flares. Now, there was a paper released earlier on this year about extreme solar flares from, I think, 13 or 14,000 years ago, which created a lot of carbon-14 in the atmosphere. So they're theorizing that the flares infinitely larger than the Carrington event that do hit the Earth from time to time from the sun. So flares, often the biggest flares occur at the back end of the solar cycle. So cycle 24, the biggest flares occurred in 2017. And if you remember, this cycle started in 2019, end of 2019. So, as I said earlier, most observed by us amateurs, and there's been more than 50 X-class flares so far to date, of which, out of those 50, I've captured 6 myself. So not too bad, really. And watch this space. So there's that, and then just a mention of the other little thing, which has now been published online. So I know we've got 1 or 2 people from different societies here. So if you go fishing about on the BAA website, my book, The Guide to Delivering Effective Education and Outreach Activities, is now free for anybody to use online, and it covers the psychological aspects of presenting, the practical things that need doing on site, such as risk assessments and all that type of stuff. And then there are quite a number of themes and resources available. Now, this is a dynamic document, and already Paul has submitted some really good ideas from yourselves, and they will be included in its next revision. I'm not sure exactly when that will be, but it is intended to be a live dynamic document. And after that, I thank you for your attention.
Andrew, thank you very much, sir. As always, I'm astounded by the images that you actually create. Yeah, I can see why you went to Spain to get them. So we're into the questions and answer session. Those people online, if you can put up a digital hand.
Can I just say one thing first, Paul?
You certainly can.
With the questions, be gentle with me.
As always, Andrew. Online people, please, a digital hand. Those people in the room could just indicate if you've got a question. And if you have, Roy will pass you a microphone. So, I'm looking for questions. We've got Andy Curtin Vaughan in the room.
Andy, just a couple of questions about the big flares that you've talked about and some of the aurora that we've seen on Earth. You mentioned obviously May 24, I think 10th to the 13th, there was a lot of activity. I think there was a lot of aurora around. I missed that one. I think I must have been sleeping. But there was a big one around the 10th of October 2024. I know you just showed some images there of some activity around a week earlier.
Yes, that
Is that
was
likely to be associated, or was it another event later on?
No, it was that sunspot that created the X9 event. Yeah, so I don't think the storms were quite as big, because what often happens with these geomagnetic storms, you can get a number of CMEs, and if they all coincide all land at the same time, they have like a magnifying effect. So you can get that, because depending on the intensity of the flare, that can depend on the velocity that the cross space. So I believe that Carrington event, it only took about 18 hours to travel the 93 million miles or 150 million kilometers between the sun and the earth. And what they tend to do, if you look at space weather, they give you a velocity of the CME as it's coming across, or they try to do.
Thank you.
Have we got any other questions? Roy Dunstan in the room. Roy, can I just ask you to move before you start speaking? So not speaking.
Hi, Andy.
Hi, Roy.
It's just a curious one. I don't know if you know. One of your early slides was on about white light, calcium light, and hydrogen light images, and saying that they're at different levels above the sun. Do you know what the difference in levels in sort of miles or kilometers they are?
Yeah, the photosphere, the visible surface, in white light, you get the upper level of the photosphere. Okay? The photosphere is about 3,000 miles thick, or a third of the diameter of the Earth's thickness. So the hydrogen alpha, I believe, you image the top of that level. Now, when you look at an image of the edge of the sun, if it's a single stack hydrogen alpha filter, all the way around the edge of the sun, you can actually physically see the photosphere. Sorry, the corona. No, start again. The chromosphere. So that you can actually physically see that, and you can see the spicules jumping up and down. So what I sometimes do, if I'm filming the edge of the sun, I will make sure that the photosphere is white, but not overexposed that much, so I can actually see all the spicules jumping up and down on the chromosphere, and obviously then the prominences above. Now, the calcium K, it's in the lower level of that chromosphere, but honestly, on hand on heart, I couldn't give you a distance of its height.
Okay, thanks, Andy.
Any further questions? Stuart? Tom, sorry.
Thank you, Andy.
Sorry.
No problem. What is it that creates the magnetic field in the sun? What's the source of it?
It's the differential rotation within the sun's level. So you've got the core of the sun, and then you've got the convection zone, and it's like a dynamo, and it's believed that the solar cycles are created by that progression of the differential rotation. And even within the layers, when you look at the equator of the sun, that has a rotation period of 27.4 days, I believe. But because we are going around the sun at the same direction as the rotation, what we observe is a 25.4 day rotational period. But when you go up to the poles of the sun, the rotational period at the poles is, I believe it's over 30 days. So all that, it causes a magnetic dynamo effect. And during solar minimum, that dynamo was worn down. And when you get these big sunspots, as they grow, they start releasing. So as they're growing, that's the magnetic energy increasing. But every solar flare is diminishing its energy and its magnetic strength. So sometimes you'll see a sunspot emerge on the eastern limb as we see it, and by the time it's gone across to the western limb, it's gone. And then others that might start emerging when they're halfway across. And if you look at observations from the Solar Dynamic Observatory, they do animations of full transit of sunspots. So you can see these things morph over a 12 or 13, sometimes 14-day period. And it's interesting seeing how they change in shape and size. It's very dramatic.
Okay, Simon. Okay. And I'm still looking around for questions. And I'm looking online. I'm not getting any. So one from me,
I can't
Andy.
find my button.
That's Loz, who suddenly started self-identifying as an ancient Greek city-state. So we'll go over to Loz.
So thank you very much for the chat, Andy. So one thing I've been looking into, sort of, instead of calcium K, I picked myself up a magnesium sort of beeline filter to look at, rather than the magnetism, start looking at the flows on the surface of the sun, especially in it's sort of the upper photosphere, and I believe it sort of covers the just below the cranial proper as well. Is that something you've ever sort of looked at, rather than just looking at the magnetic activity, which obviously calcium K is sensitive to, looking at the velocity and oscillation fields?
Simple answer, no.
Oh, fair enough. In which case, how about this? Instead of me asking my question even further, I'll bring it along. Let's have a play.
Yeah, and I have seen people, sometimes they go off band with hydrogen alpha, and people use Doppler shift as well for
Yes. Well,
for the flow on the surface, but it's not an area that I really wanted to investigate. When I came over here, I got certain objectives, one of which I wanted to film some X-class flares. I think I've done 14 of them now. I wanted to get magnetic loops, which I've done a lot, and I wanted to do a lot of animations of the flow in the photosphere in white light. And with white light, we call it white light, but we tend to use a green filter. And by using that, you're narrowing the waveband down. Because if you try to focus all the lights in white light, you can't get a good stable image. So anything we can do to improve the stability of the image. And the other thing we try to do is capture a lot of frames in a short period of time. So if you've got a very quick frame exposure, like say example, a 3,000th of a second, or sorry, 3/10,000ths of a second, the sun hasn't moved much because it's continuously moving. So if you can say capture all your frames within 15 or 20 seconds, that feature, particularly on prominences, does not move that much, so you can get a sharper image. But what we tend to do,
fair enough. That's kind of led into what my question actually was. We're sort of trying to pick your brain based on your experience, based on everything that you've been doing with hydrogen alpha and calcium K, because obviously calcium K and magnesium are looking at the same area. It's just one's focusing on magnetism and the other one's more focusing on oscillations and Doppler shifts. But they're actually looking at the same area of the sun, and sort of I was trying to lead on because of the similarities. If you had come across it, is there any advice for sort of how we should be imaging?
What we tend to do, Loz, is on Solar Chat, there's lots of people that specialise in different areas. So there's no reinventing wheels. Everybody shares the knowledge, and everybody, including myself, we've all come on together. Now, what you can get is you get aperture fever, and also you get bandwidth fever. So I'm down at about 0.3 of an angstrom with hydrogen alpha and about 2 angstroms with calcium K. You can tighten that down, but the more you tighten it down, the less light you're getting. And also, in white light, in the ob, you've got a C14. And with a full width Barder filter on that, you should be able to do, if the atmosphere is stable enough, you should be able to try imaging at maybe 10 meter focal length on sunspots, which you'll get some really nice convection cells and detail within the sunspot and penumbra. All the best white light images I've seen have been with mainly C14s. But some people have gone to 300 millimeters with hydrogen alpha and calcium K, which gives you really, really high resolution images, but you're looking at a really, really small area. And when they've caught an X-class flare, they've had to do 3 images to get the whole thing in, which doesn't give them any opportunity of doing so you've got to decide what you want and then go for it, because there are so many different parameters that you can look at and change.
Cheers for that. Yeah, I got it.
Okay, I don't know whether anybody else will hear me, but I just would ask if I can ask you to clarify something that confuses me a lot with solar stuff, and that's which is east and which is west. You stated that the sun rotates east to west, but it rotates the same way as the Earth does, which is west to east. And in fact, as I understood it, the definition of east and west is now such that every object in the universe rotates west to east, But is the sun an exception? I mean, this anomaly was sorted out for the moon, some years ago now, when the directions were all reversed. Do I take it that the directions on the sun are still, as it were, backwards, and it does rotate formally east to west, or have I got that all wrong?
Well, all I can say, I am now confused as well, Peter. I'm going to have to check that.
Oh, I'm sorry about that.
Yeah. No, because the sun is denoted as the eastern limb, which is on the left-hand side of all the images I show and all the space satellites show, which is opposite to how we think of on Earth, isn't it?
Yes, yes.
It's opposite. Yeah, and the sunspots appear on the eastern limb, and as it rotates round, it goes off the western limb of the sun. So I just stick with what the scientific convention tells me. But it is like you say, if you look up a map of the Earth, east and west is all the way around.
That's right. Yeah.
Yeah.
I mean, the anomaly exists on quite a lot of places in the universe. I mean, you talk about double stars, the eastern ones on the left, and that's because of the directions in the sky, and that's the way all objects were done at one time. But I say that it was then realized that you had this anomaly for the moon, that it rotated the same way as the Earth does, but east to west instead of west to east.
Yeah.
And the same thing applied to the sun, but the anomaly remains, you think.
Yeah.
Okay, thanks, Andy.
Cheers, Peter.
Okay, hopefully you can hear me now. My USB microphone or my Bluetooth microphone ran out of power, and I've just swapped over. Jez Robinson, online, please.
Can you hear me there, David? Dave?
Yeah, yes, we can hear you, Jez.
Yep. Cheers. Thank you. Yeah, Andy, it was a question about height. Really, it was about looking at the umbra and penumbra. It almost looks volcanic in the nature of the umbra looks like it might be higher than the penumbra, and I just wondered whether any studies have been done on whether there was a height variance in sunspots.
There is,
granules.
And it's called the Wilson effect.
Right. Sorry if you mentioned it earlier, but
yeah, when you come, if you look at a sunspot, you have to look at the ones that appear symmetrical. So normally the single sunspots, and when you look at the Wilson effect, the penumbra on the leading edge is wider than the far edge, which is the one nearest the edge. But that appears to show that some sunspots appear to be a slight depression in the surface, as if the umbra is lower altitude.
And do we know by what sort of magnitude or height?
No, I've not seen any papers discussing that height, but that doesn't mean to say that they don't exist.
I mean, the darkness of the umbra is caused by the magnetic fields taking the energy away, is it? Or?
It is, yes.
Yeah. Okay. Cool. All right. Well, maybe one day somebody will find out. Yes. Great talk. Thanks.
Okay.
Cheers.
Thanks, Jez. I'm looking around for any more questions. Nothing from our visitors. Oh, we have got something. You'd just like to introduce yourself as well.
Yeah. Yes, I'm Henry.
Hi, Henry.
Is it going back to that thing about mirror? Your right is on your left. Or yes.
Paul,
Is it partly?
I think that microphone's turned Henry into Norman Collier. I'm not getting anything.
Yeah.
Henry, is there a green light on the front of the microphone? That's the first thing. And are you speaking into the microphone or into the USB connector?
Yeah.
You got it the right way. Okay. Just hold it a bit close to you.
Yeah. It's the east and west. You have to think of it as if you're sitting on the sun rather than watching it from the Earth.
Yes.
The east and west.
Yes.
So it's a mirror. It's like when you look in a mirror, something going round goes the opposite way to what it would be if you were on the item. Yep.
That's one way of explaining it, but
Andy,
yeah.
from what I know, if you went due north from the pole of the Earth or from the pole of the Sun and look down, virtually everything rotates anti-clockwise. And then you look at the Earth rotates anti-clockwise, the Moon goes around the Earth anti-clockwise, Mars goes around the Sun anti-clockwise, Phobos and Deimos, etc., the Galilean moons, everything is virtually anti-clockwise. All right, you've got strange things like Venus, which actually rotates clockwise, and Uranus that's tipped over, but virtually everything else is anti-clockwise. And that applies to the sun's rotation as well.
Cheers, Roy.
I think that closes the matter. All right, Henry. I think I'm just going to ask one question, and that is, you've been in Spain now 14 years. You went out there with a set of objectives. You are ticking them off regularly. Graydon, have you any further ambitions or ways that you might things that you might want to explore?
I try not to limit my mind or what I believe I'm capable of doing. So
I was just limiting it to your solar observations, Andy.
Yes, I've got one I've not ticked off. I have not imaged a super flare. Anything above X10. The biggest I've imaged were an X8.3, which was the second largest flare of cycle 24. And I didn't think there were any super flares on cycle 24. But when I've done some research for this, there appeared to be an X13, which I can never ever remember that occurring. And now I've been monitoring it all the time, but space weather seems to have picked it out.
Well, good luck with that. I hope you get a super flare in the relative near future. Got to leave you working away there. I think we'll leave it there. I did questions and answers, and it just leaves me to invite everybody to join me in giving you a big Mex Princeton Astronomical Society. Thank you, ladies and gentlemen. Andy Devey. Thank you very much, sir.
Thank you.